Hi, in this video we will step through the execution of a couple of search algorithms on a few examples. The first algorithm we'll consider is depth-first tree search. While we step through it, we'll visualize the algorithm using the search tree visualization. Here's our state space graph, which defines our search problem. We even have costs annotated on the edges, but remember, for depth-first search, they will not play a role. They're essentially just distractors for now. We have a start state, which is denoted by S, and a goal state, just a single goal state denoted by G. When we look at how the search tree will evolve, running depth first search, alphabetical tie breaking, we start with just the root node, S. Then, when we call the successor function on S, we get two children, A and B. And remember, really these children are not just A and B, but they are a plan to start in S and go to A, and a plan to start in S and go to B. Then, once we are in A, which is alphabetically first compared to B, we will, after expansion, get C and B. Again, these are not just C and B, these are really partial plans, so what you have here is the plan to start in S, go to A, and then go to C, and the plan to start in S, go to A, then go to B. Depth first search always looks at the things deepest in the tree first. There's two of them that are equally deep. Amongst the ones that are equally deep, it does alphabetical tie breaking. B comes first alphabetically, so now it'll expand B. B has just one successor, C. So now we have C here. Again, this is not really just C, but it is a plan to start in S, go to A, go to B, and then go to C. As the next node to expand, we'll pick this one here because it's the deepest one in the search tree. And when expanding this one, we get just one successor, G. Again, this is not just G that we have in the search tree here. It's really the plan to start in S, go to A, go to B, go to C, and then go to G. Now the deepest one in the search tree is this node over here. Expanding this node, what we see is that the last state in this plan is the goal state. That means when we are expanding this, we actually don't have to expand anymore what we declare success. And the path found is SABCG. Now let's again look at depth first tree search, but do a priority queue visualization. Priority queue we'll use as its priority depth in the search tree, which corresponds to the number of steps in the plan. Okay, so as always we initialize with the start state. So our priority queue consists of just S with a priority of 1. Only one element in the priority queue, so that's the one that gets taken out. When we take out S from the priority queue, after expansion, in our priority queue we have the elements A and B. It's not just A. This is really going from S to A. And for B, also it's not just B. It's going from S to B that we have on our priority queue. For SA, the priority level is 2. And for SB, the priority level is also 2 because there are. We'll do alphabetical tie breaking, which means we'll expand this one first, the one going to A. We'll take this element out and expand it. A has two successors, B and C. So we'll add two elements to the priority queue. There will be SAB, and the priority there will be 3. And there will be SAC with a priority also of 3. And we will retain SB, looking for expansion again. The nodes with the highest priority, higher numbers, higher priority for depth first search. It's the 3s here. Alphabetical tie breaking makes us go with this one first. B has only one successor, C, so we have SABC. This has a priority of 4. The other two, SAC with priority of 3, and SB with priority of 2. Next one to expand, well, the one with the highest priority here is SABC with priority of 4. C has only one successor, G. So after expansion we get one successor, SABCG. this has a priority of 5, and the other two remain on the queue as they were. The next one to expand is this one here with a priority of 5. When we are about to expand this, we realize that when the last state here is G, which is the goal state, so we actually don't have to expand anymore. We can declare success. The path we found to the goal is the one right here, SABCG. Now let's look at breadth first tree search, and we'll do the search tree visualization. We have the same state space graph here. So the search tree will be initialized with the start state. Then when calling the successor function on the start state, we get two successors, A and B. Remember, these are really plants, not just states that are associated with the nodes in the search tree. So SA and SB. Then breadth first search will look at the shallowest nodes in the tree that haven't been expanded yet. There's 2 of them. It'll do alphabetical tie breaking, so SA will get expanded first. A has 2 successors, C and G. So we'll get SAC and SAG. Next, breadth first search will expand again, the one that is shallowest in the search tree that hasn't been expanded yet, which is this node over here. And B has 1 successor, C, so expanding this one leads to SBD. Performing alphabetical tie breaking, who's next? This one here. Expanding SAC, we get just 1 successor for C, we get SACG. Now, these are the 2 shallowest in the search tree. Alphabetical tie breaking tells us to go with this one next, SAG. When we ask for expansion of SAG, we notice that the last state is the goal state. That means we declare success. We found a path to the goal. And the path we return is SAG. Now let's do a visualization of our step through using priority queues. So our priority queue gets initialized with just the start state, S. The start state is at level 1 in the search tree. There's only 1 state that participates in this plan. So priority of 1. That's our initial priority queue. Expanding it, there's 2 successors, A and B, so we get the 2 successors onto our priority queue, SA, SB, and both of them have a priority of 2. Pick the one with the lowest number. Both of them have 2 alphabetical tie-breaking picks. This one next. So next our priority queue will be placing that one with its successors. A has 2 successors, C and G, so we get SAC, which will have a priority of 3. We get SAG, which has a priority of 3, and we retain SB, which has a priority of 2. 2 is the lowest number. Breadth first search will go for that one. Expanding, keeping the others, we get SAC with priority of 3, SAG has a priority of 3, then B has 1 successor, C, so we get SBC with now a priority of 3. That's our new priority queue. The lowest number here, which is what breadth first search will look for, is 3. Alphabetical tie breaking puts SAC first, so expand that one. C has 1 successor, G, so we get SACG, which is a priority of 4. We retain the other 2. Now who's next? The 3s are the lowest numbers. SAG is alphabetical before SBC, so we have SAG first. Oh, last one here is a goal state. That means we declare success, and we return SAG as our path found by a breadth first tree search.